The learning objectives for this lesson include calculating bulk density and porosity. You do not need to calculate particle density of a soil, even though it says so on the slide. Again, you do not need to calculate the particle density of a soil. For forest and agricultural landscapes, we want you to explain how management practices affect bulk density and porosity. We're going to contrast macropores and micropores as to their size, characteristics, and impacts, and we're going to have you calculate percent porosity. You do not need to explain the reason that the levees were doomed to fail. So let's quickly review soil texture, the surface area in a teaspoon of soil, and doing the math. Now remember, the smaller the particle size, the more surface area we have to interact with things in the soil, like water or soil nutrients or plant roots. So sand, even though it has a larger particle size, it will have a smaller surface area, whereas clay, which has a smaller particle size, will have more surface area. Remember, there is an inverse relationship with particle diameter or particle size and its surface area. Now, when we talk about density, we're talking about the mass per unit volume. So using water as a reference, we have 1 grams per centimeter cubed of density for water. Other examples include pine wood, which have about 0.7 grams per centimeter cubed density, quartz, which has 2.65 grams per centimeter cubed density, and steel, which is much denser, which is why it's so much harder, which has 7.7 grams per centimeter cubed density. So when we start talking about soil material densities, I want you to understand that organic materials have much less density, which is why they feel so fluffy. Whereas mineral materials have a range of 2 to 5 grams per centimeter cubed in density. But what we're going to use for soil particle density is 2.65 grams per centimeter cubed. So this is our constant for this class. Whenever I ask you to calculate anything that involves soil particle density, you will always use 2.65 grams per centimeter cubed. So again, particle density that we're going to utilize in this class is 2.65 grams per centimeter cubed. Please remember this number. You will need it for various calculations. Now, bulk density is the density of soil in a natural state, including pore space and organic matter. An oven-dry sample weight is used for this calculation. Before I go into what the calculation is and describing what the actual formula is, I want to briefly mention that essentially bulk density is weight per volume. So if you're looking in a classroom full of people, and let's say there's 60 desks, but there's only 10 people, our bulk density would be very low because we only had a few people occupying a very large space. But if we were to add, say, 200 people to that room, which we wouldn't do because Rona, but anyways, if we were to add 200 people to that room, which normally only holds 60, we would have a very, very, very high bulk density. It would be very dense, and it would be very hard to move from one room to the other. If that were the case, it would be very hard if we were to, let's say, compare this to soil science, which is what we're learning in this class, so it makes sense, right? But let's say we had a really, really high bulk density in soil. It would make it very, very difficult for water to move through soil, or nutrients to be moved through soil, or roots to grow through it. However, if bulk density is low, then everything's peachy. So this is why we think bulk density is important to know and understand, because it has such a huge impact on how everything moves through soil and how we can manage it. So when we're calculating bulk density, which you will have to do, we take the dry weight of a solid in grams and we divide it by the volume of soil. So if I were to give you the dry weight of a solid and the volume of the soil, you would take that dry weight and you would divide it by the volume. And that's how you calculate bulk density. And that will be on your exam, I promise. So factors that affect bulk density. Soil texture influences bulk density. Organic matter content makes bulk density fluffier or smaller. Bulk density changes with soil depth. We find that bulk density increases as we go deeper in the soil, and that's because organic matter content falls as we go deeper in the soil. And generally speaking, we get heavier textures the deeper we go. More clay is present. Traffic increases bulk density. It causes compaction, which means that we're squishing more particles per unit of volume, and that increases bulk density. We have very few pore spaces. However, in the topsoil, which tends to have a lot more organic matter and a greater, stronger development of pore spaces because of smaller structural units, we have a ton of pore space, comparatively speaking. Now, we've talked a lot about pore space. Let's actually start defining the individual pores. We have two types of pores in soils, macropores and micropores. Macropores are more than 0.08 millimeters in diameter, whereas micropores are less than 0.08 millimeters in diameter. We tend to see soil aggregate into microaggregates with micropores in them, and in between those microaggregates are where the macropores generally are. So here's some example calculations for bulk density, which we're also going to show you in lab, and I think next week or the week after. So the first thing we have to do to calculate bulk density is to actually go out and take a core sample. Now, knowing the shape and size of the core, like height and diameter, allows us to calculate the volume of the core used. In this case, the height of the cylinder was 12 centimeters, the diameter was 5 centimeters, giving us a radius of 2.5 centimeters. What this ultimately gives us, using pi radius squared height to calculate the volume of the cylinder, is a volume of 235.6 centimeters cubed. To calculate the bulk density, we know that we need to take the oven dry weight of the material that we collected and divide it by the volume. So we take our 330 grams and we divide it by our 235.6 centimeters cubed, shown here, and we get 1.40 grams per centimeter cubed. To calculate the pore space for this sample, we basically take the bulk density and plug it in right here, and we divide it by particle density. Now remember, particle density is 2.65 grams per centimeter cubed. That's our constant. So if you take 1.4 divided by 2.65, multiply it by 100. Hold on, I'm giving you time to get your calculator out. 1.40 divided by 2.65 is 0.528. Multiply that by 100. 52.8, subtract it from 100. And yes, I know you get a negative number, ignore that. Pretend there wasn't negative. We end up with 47.2% pore space. If you follow that guideline every time, you'll always get it right. Just remember, it's not a negative number. Order of operations, and then it won't be negative. Now, I have a question for you. Is there more total pore space in a clayey or sandy soil? I'll give you a second to think about it. All right, time's up. What's your answer, folks? Well, we know that sand particles in a known volume don't have as much surface area, which means they're not going to have as much pore space as smaller particles that have all those little tiny micropores in them. So ultimately, clay ends up having more pore space. Now I want you to think about differences in straws. If you go down to that delicious place in the village and get a poke bowl, then you get those giant boba straws, right? Those are the kinds of pores that we're going to see in sand particles or in sandy soils. I want you to imagine that you're holding a handful of those for a second. Now, comparatively speaking, have you ever seen those little red straws that everybody uses to mix coffee at large gatherings? And inevitably, as a child, you tried to drink hot chocolate through them and burned the ever-loving crap out of your mouth? I want you to imagine yourself holding a giant handful of those. Ultimately, those tiny straws are going to move way more surface area worth of anything because they have way more pore space. Even though they're tinier and they don't look like they have as much, we know that there's an inverse relationship between particle size and surface area. So ultimately, micropores end up having more pore space. Remember this because it becomes important in the water chapter later on in class. Clay has way more pore space. So here's an example of how texture has an effect on pore space. This graph shows percent pore space from 0 to 70% on the left axis, whereas down here we see clay texture, loam texture, and sandy loam. The top part of each bar graph shows the percentage of micropores, whereas the bottom part of each bar shows macropores. So we can see that clay has significantly greater percentage of micropores. Loam has half and half, and sandy loam has very few micropores, but a lot of macropores. So clay is going to have much more pore area to move anything. Sandy loam is going to have much fewer pore space to move things. Loam is the perfect mix. So now we're going to start applying the importance of bulk density and soil porosity. Why is bulk density and porosity important? It helps us determine aeration status, engineering properties, root penetration. Yields increase as bulk density decreases, which means as bulk density decreases, soil gets more fluffy, which means plant roots can move through it so much easier. That means that ultimately they're going to be getting more nutrients and growing deeper, which means they're going to grow much more fruit above the surface, which is why we see yields increase. However, where bulk density is high, we see a lot more plant disease. And that's because the soil is compacted and it's really hard for roots to move through. So just like you get during finals week, you get stressed out and you get sick, plants get stressed out when they're in compacted soil and they're more likely to be susceptible to plant diseases. So we see plant disease higher with higher bulk density. In review, you've learned how to calculate bulk density. We know that particle density is 2.65 grams per centimeter cubed. Ignore the typo on the slide. It should be 2.65 grams per centimeter cubed. And porosity is the bulk density divided by particle density times 100, and all of that is subtracted from 100. So in this example, we know that if we have an oven dry weight of 330 grams and a volume from the sample collection of 235.6 centimeters cubed, bulk density is 330 grams divided by 235.6 centimeters cubed. And the bulk density ends up being 1.40 grams per centimeter cubed. To get the particle size, to get the porosity of that, we take the bulk density, 1.40 grams per centimeter cubed, and we divide it by 2.65 grams per centimeter cubed, which is our constant particle density. Multiply that by 100 and subtract all of that from 100 to get 47.2%. There's some examples in the study guide for exam 1. Please work some of those out, and if you have any questions, we can meet virtually or in person to go over them. I must really find this slide important because I've put it in here 3 times. So hey, let's go over it again for fun. Bulk density and porosity, they're important because they tell us aeration status, engineering properties, root penetration. Yields increase as bulk density decreases. Plant disease is higher with higher bulk density. I guess you must know this for exam 1 or something. Hint, hint. I'm going to skip this. Let's go over structure formation and management. There's factors that influence aggregate formation and stability. First is physical chemical processes like mutual attraction among clay particles. They stick together, very much so, which is why it's such a sticky texture. There's shrinking and swelling of clay masses, which also gives rise to aggregate formation and stability. And then there's biological processes, activities of soil organisms. Worms literally eat dirt and poop it out with glue coating. We also have the influence of soil organic matter, which is basically like soil's personal form of glue to allow it to adhere to each other. Back to that physical chemical process, that mutual attraction among clay particles. Flocculation is when soil particles are attracted to each other and they collect in groups. Now, there's definitely a role of adsorbed cations, meaning adsorbed to the surface like a Post-it note, not like absorbed like your abs, but adsorbed like a Post-it note at the surface. This is important for the formation of microaggregates. One example is pseudosands, which have a cementing action of iron oxides in ultisols and oxysols. Flocculation and dispersion. All right, so flocculation is going to occur when we have a lot of divalent and trivalent cations present. So divalent meaning calcium, which has 2+ charge, that's divalent. Iron 3+ charge is trivalent. Aluminum 3+ charge. All of those neutralize surface charges and cause them to stick together. Whereas monovalents, like sodium +1, cause dispersion, where things blow apart and no longer adhere together. And to help you memorize this, I'm going to give you a really disgusting analogy. Okay? Don't eat during this analogy. Okay? All right. So let's say you go to the fair and you eat all of the fair food. Okay? It's loaded in sodium. And your tummy starts grumbling because all that sodium has caused all the things moving through your intestines to disperse, and then you get diarrhea. Who are you going to call? You're going to call Pepto-Bismol. Why are you going to call Pepto-Bismol or Tums or any of those? Because they're stock full of calcium. Calcium, being a divalent ion, rocks through your guts and helps bring it all back together so you have solid turds again. You're welcome. You'll never forget the difference between flocculation and dispersion again. And maybe never want to eat fair food either. I don't know. Probably just still eat fair food because it's delicious. Deep fried Twinkies, anyone? Elephant ears. Sounds so good. Cotton candy Mountain Dew. Oh, it's my favorite. Anyways, moving on. Here's a great example of kaolinite flocculated in stacks. Isn't it pretty? All right, so in vertisols, we see a lot of shrinking and swelling. As clay soils dry, the cracks develop on planes of weakness, and over time, this gives specific shape to soil structural units. We're going to talk now about aggregate formation and stability along the lines of biological processes, which includes the activities of soil organisms and the influence of soil organic matter. Soil organisms like bacterial polysaccharides and glomalin create or assist in the formation of macroaggregates. They're literally little pieces of glue, okay? And they stick things together around roots and form aggregates like granular. Granular structure is a great example of how this happens. So why do we care about organic matter and these biological processes? Well, organic matter is a major agent in temperate soils, and it provides a substrate for microbial activities. So over here on the left, we see two soils. They are dry soils. There's a high organic matter one, and there's a low organic matter one. Now, we're about to find out why we care about having high organic matter in our soil. See, we added water, And the high organic matter soil stayed together because it had that awesome organic glue keeping the structural units in place, which means that all of those pores that formed between and around those aggregates are free to move water. However, our sad panda little low organic matter soil over here on the right fell apart. All of the individual soil units that fell apart now have clogged all the pores. The water can't move through. There's penguins crying somewhere, probably, or pandas. I don't know. Choose whichever animal you want. Water's ponding at the surface. Erosion's gonna happen. Everyone's sad. It's time to go home. Here we can see the influence of organic matter where the aggregate on the left doesn't have very much organic matter. It's giant and clumpy and sad. Whereas the one on the right, it's healthy and happy and fluffy, and lots of roots are able to grow through it, and things are flourishing, and there's sunshine and rainbows, and probably coronavirus is gone in its world. Maybe. It would be nice. Structural management of soils. Tillage and the preparation of a good seed bed. Well, originally, tillage started because we thought that if we made the soil really loose, it would help for root growth and seedling emergence. We wanted it firm enough for good seed to soil contact, which is true. It does help with seed to soil contact and moisture uptake. And we wanted to break free of large clods. Now, I'm going to burst your bubble and I'm going to let you in on a little secret. It's not so much a secret anymore. Tillage is not very good for the soil. Now, before you go hating on all the farmers who still till, I need to tell you a few things. First of all, farmers started tilling in the early 1800s because they mistakenly thought that the smaller you made soil, the easier it would be for plant roots to literally eat it like hungry, hungry hippo, eat the soil, take it in their plant root, get whatever they wanted, and then spit it out. We later found out that's not how it works. We later find out that roots don't have mouths that eat soil. Instead, roots have tiny, tiny openings and they exchange cations on the surface of soil particles through those pores, essentially. So the smaller the soil size, it doesn't matter. We don't need to pulverize soil to get the cations off the surfaces of them. In fact, we found that the more we till, the more we destroy structure, the more we decrease organic matter, the more we cause erosion, lots of bad things. However, there's lots of people in the industry who still haven't made the switch because it's a very expensive switch to make. You see, a tractor and a planter can cost hundreds of thousands of dollars, and switching over to that kind of equipment can be very expensive, and it just takes time to save that kind of money. So we've seen a lot of people make the switch, but there's still people lagging behind, and we don't want to be mad at them or upset, but education is key for farmers, and that's why we have extension agents and people like me teaching this awesome class, because one mind changed away from tillage at a time is one more soil organism left in the soil to create organic matter to make the world a better place. All right. I don't care about this table, so I'm going to skip it. All right, soil crusting is what happens when we have overworked and underprotected surface soil aggregates. And we have a heavy rainfall event come through, and those individual soil drops literally hit the surface of the soil like a fist to a punching bag, just bam, 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 creating an impact surface and sealing it, literally stomping it until there's a thin crust that water can't get through. And as it dries, this crust kind of develops, well, a crust. So you'll often see examples of this along the edges of lawns where, inevitably we all cut the corners on sidewalks and walk across like the corner of the lawn. And then you'll start seeing that area of grass die. And later in the fall, when things like start drying up, it starts peeling up a little. It has like a weird little crust. That's what crusting is. So ultimately, to manage soil tilth, we need to minimize tillage, time our traffic so that we're not walking on soils when it's wet. We need to mulch the surface with lots of things that will provide organic matter. We need to add crop residues and animal manures to build back that organic matter. We could include rotations of sod crops, some kind of grass to add fibrous roots through the soil. We can use cover crops and green manure crops. We can correct pH problems. All of these things are good for the soil.